This is Group 2B's Investigating Resistive Forces project. Our group was investigating proportionality constants of 3 different liquids by calculating them from acceleration velocity graphs in order to see the relationship of terminal velocity and viscosity. We hypothesized that proportionality constants will be able to be calculated from these graphs' trendline equations. Corn syrup will have the highest proportionality constant and lowest terminal velocity, and isopropyl alcohol vice versa. We concluded that corn syrup did have the lowest terminal velocity inversely related to the proportionality constant, but water had the highest terminal velocity.
So here's our system schema of the situation involving the ball, the fluid, and the earth. It's important to note that the main interactions acting on the ball are contact with the fluid and gravity with the earth. When we look at the free body diagram of the situation, we'll notice that there's 2 forces at play here on the ball. The first is the force of gravity, and then we also have the force due to viscosity. Now the force of viscosity changes over time with velocity. So initially the velocity is 0, so the viscosity is 0. But as the velocity increases, so does the force due to viscosity. This is different than macroscopic friction because friction is independent of velocity while viscosity is proportional to velocity. So initially, the velocity of the ball is 0, so the only force acting on it is the force of gravity. As the ball gains a little bit of velocity, the force of viscosity comes into play, acting in the opposite direction of gravity. As the ball continues to gain velocity, the force of viscosity continues to increase. And then finally it gets to the point where the force of viscosity is exactly equal and opposite of the force of gravity. And so with using Newton's second law, we can say that the acceleration of the ball is 0, and we've reached terminal velocity where Fg is equal to Fv. It's important to note that with our reference frame, down is positive here and up is negative.
Our experiment aimed to see how different fluids affect terminal velocities. To achieve this, we used the same metal ball bearing in 3 different liquids. We conducted our experiment by first holding the ball above 3 liquids. From here, we started recording on our phones, then proceeded to drop the ball. We stopped the recording once the ball hit the bottom. We then transferred the video into Tracker Pro. Tracker Pro, we track the ball's movement to create various different graphs, including velocity versus time, acceleration versus time, and acceleration versus velocity. The acceleration versus velocity graphs were used to determine viscosity constants and terminal velocities.
These are our velocity time graphs for each of the 3 liquids. Velocities of all are decreasing over time, as you can see. This is because the initial velocity was higher than the terminal velocity when the ball initially reached the liquid. Therefore, velocity had to decrease to reach terminal velocity. These are acceleration time graphs, ideally with enough points. You should see a start at positive 9.8 meters per second squared and a decrease until terminal velocity is reached. However, some of our trends were different, which we will acknowledge shortly. And these are our acceleration velocity graphs.
So again, our net force acting on the ball is the force of gravity minus the force of viscosity because down is positive. Using Newton's second law, we can rewrite this in terms of mass and acceleration, and then this equation can be rewritten to correspond to the equation of a line, where y is acceleration and x is velocity, and the viscosity constant is proportional to the slope of the best fit line. As you increase the slope, the viscosity constant increases because everything else in the slope is the same. Therefore, you can use the slopes of the trend lines to compare the relative viscosity constants of the fluids. The relationships we found were consistent with literature values.
Terminal velocities were calculated using the previous equation, and when terminal velocity is hit, acceleration equals 0, so you can set this equation equal to 0 and then solve for x. Terminal velocity was found for all 3 liquids, as you can see here.
The first limitation we identified was our initial ball drop being in the air. This leads to initial velocity in our liquids not to be 0. Our initial velocity not being 0 led to our accelerations being negative to bring the ball's speed towards terminal velocity. The second problem we saw was limited data points, so clear trend lines were hard to see. Our equipment couldn't slow the ball down enough to see a definite ball, but instead we saw a blur. Lastly, our balls traveled a very minuscule distance. The only one that could reach terminal velocity was the ball in corn syrup. The experiment we conducted was slightly different than our model because the initial velocity of the ball exceeded terminal velocity. Other sources of error also affected our data. Nevertheless, we were able to determine proportionality constants for our data for various liquids that were consistent with the actual relative viscosities of the liquid.